OSPF is the most common dynamic routing protocol used inside the autonomous systems. In one of the previous videos in the channel, we went through the single OSPF configuration. In this video, we'll expand that to cover multi-area topologies. So we'll go step by step. Welcome to the network trip. Before going to the lab, we need to understand why a multi-area design can be a better solution in some environments. And also, when a single area OSPF topology is going to be the best option. If we're dealing with just a few routers, a single area is going to perform pretty well. But if we are dealing with dozens or maybe hundreds of routers, executing the algorithm to calculate the shortest path to reach every network is going to degrade the performance, since it's going to be using the CPU and RAM memory in those devices. The multi-area design in OSPF is going to reduce the CPU usage by creating several link state databases. Every area is going to have its own link state database. But what is exactly an area? An area is basically a group of router interfaces. So we see the diagram that we have here on the screen now. We can see that we have 5 routers and we have 3 areas. We have the backbone, we have the area 1, 0.0.0.1, and then we have the area 2, 0.0.0.2. We can see that some of those routers have one interface that is connected to one area and the other interface is connected to a different area. And that's why we are saying that an area is a group of router interfaces. So basically the areas are at the interface level. For example, if I see here R2 is connected to the area 0 and also is connected to the area 1. So R2 doesn't belong to any specific area. The ones that belong to an area are the interfaces on it. When we are designing the multi-area topology, we have some limitations. One of those is that all the areas must be connected to the backbone area. If we check the design that we have here on the right, we have the backbone area at the top. And here we have area 1 and also we have area 2. And we can see that we have one router that is connected to the area 0 and to the area 1. The same thing is happening with the area 2. R3 is connected in one interface to the area 0 and a second interface is connected to the area 2. So we have those 2 areas connected to the backbone. It is not possible to successfully exchange routes and have an area that is not connected to the backbone. For example, if I add a new area here and I add a router and this router is connected to the area 1 and this were the area 3, so basically that is against the OSPF definition and we can't just design the network like that. There is a workaround that we can use and we'll be covering one of the upcoming videos here in the channel that is called a virtual link, that basically can create a virtual link between this router and that router, and then this area can be used as transit to establish the adjacency between area 3 and the backbone. But this is not the best solution. If we are designing the network, we'll try to have all the areas connected directly to the backbone area. And finally, before going to the configuration process, we'll talk a little bit about this guy here, the ABR area border router. The router is going to be connected to 2 areas. One of those is going to be area 0. The second area, it can be any other area. For example, if we check those requirements, in this diagram, I can identify 2 ABRs. So that is going to be one ABR and R3 is the second ABR. And that is because one interface is connected to the area 0 and another interface is connected to any other area. So that's basically the area border router. That device is responsible for sending all the information from the area 1 into the backbone area, and then receive the information from the backbone area and inject that into the area 1. Additionally, that device is going to have two link state databases, one from area 0 and one from area 1. So first of all, we need to create a router ID. For doing that, we'll create a loopback interface. This is just going to be an empty bridge. Then we'll assign an IP in that loopback interface. In my network diagram, I'm going to use that format. So 10.255.255.x, where x is the router number. Then we'll create an object that is the router ID that is optional, but is a good practice. So we can do that in routing router ID. Then we'll create the OSPF instance that is on the routing OSPF and instance. Then we'll add all the areas that are required in the current router. And finally, we'll create the interface templates. And finally, we can verify and test. So I will go through that configuration process. Basically, at this point, I have configured the IP addresses in every interface in those routers. Additionally, I have created the loopback interface and also the router ID object. I will go from steps 2 to 4 in every router. So I will show you the configuration that I have now in every device. So I have the Winbox over here. So we have R1. If I go to bridge, we can see that there is one bridge that is called loopback, and then there is an IP address on it. If I go IP addresses, we can see 10.255.255.1. Then we have the IP on the interface that is going to the switch, and this is the management IP. So you don't need to do that. You are working with a physical device. But in my case, if we check the topology, you can see that I have that computer. This is my host computer that is basically managing that device. And that's why I'm getting that IP address. That is not part of the OSPF domain in this case. Additionally, I have a router ID object. This step is optional, but I like to create that in routing and then router ID. You can see that I have that object and I have assigned the IP that is on the loopback interface. Exactly the same configuration is in R1, 2, 3, 4, and 5 in all the routers. So let's go with the step number 2, create an instance. So that is on the routing OSPF instance. So I will do that process in all the devices simultaneously. So let's go with R1. So R1, we go to routing OSPF, then instances. Basically, we're going to enable this process in this device. So I'm going to add a new instance. I will keep the default name. Version is going to be 2 because I'm running IPv4. BRF, that is going to be the main BRF. Router ID, I'm going to pick the object that I created previously. And the routes from this instance will be injected to the main routing table. That's all I need here on the instance. And now let's go from R2 to 5 with exactly the same steps. So routing OSPF, let's add an instance, router ID, routing table main. Same thing, R3, instances, router ID, and the main routing table. Now R4, routing OSPF instances, ID, and the main routing table. And finally R5, routing OSPF instances, the router ID, and the main routing table. So the OSPF instance is running in every router. Now we can go with the next step, step 3. Create areas required in the current router. So here I'm missing an R, so this is router, not route. So let's start with R1. So R1 is connected just to the backbone area. So that means that R1 requires only one area. So let's go to R1 areas, and I'm gonna add the area 0. The ID all zeros, and I can click OK. Now, if we check R2, R2 is connected to area 0 and area 1. So I will need to add those two areas. So let's go to R2. Let's go to R2 and then areas, and I'm gonna add those two. So area 0 and the next one, area 1. If we check R3, this is connected to the area 0 and also to the area 2. So let's do that. R3 areas, and let's add area 0 and the next one, area 2. And the next one is R4 that is connected just to area 1. So here we don't need the area 0, so we'll add just area 1. That's in R4. Let's go to areas. Let's add a new entry, area 1, and OK. And finally, R5 is connected just to area 2. Areas, area 2, and the area ID 30.2. So now we have completed the step number 3. We're just missing one step in every router and OSPF will be running. So basically it's a pretty simple process, the new way how we configure OSPF in Mikrotik devices. So the interface templates. So basically here the idea is that we need to enable OSPF at the interface level. So we need to identify the interfaces that will be sending OSPF messages. If we have interfaces that have networks that we need to advertise, then we can add those interfaces as passive interfaces. So we need different types of interface templates. Additionally, in this interface template, there is a property that is the network type that plays a big role in OSPF. So if we are just expecting one neighbor in the link, we can use what is called point to point. If we are using point to point, we won't have the designated router and the backup designated router. Additionally, we can have broadcast. We are expecting more than one neighbor, like for example, in that area. So you can see that all of those devices are connected to the network 10.0.0/24. So R1 is expecting 2 neighbors out of that link. In that case, we'll need a DR and a BDR. So those links are gonna be broadcast, and those links here will be point to point. Additionally, those interfaces there will be passive interfaces. That means basically that we are not expecting OSPF neighbors out of those interfaces. So let's go to R1 and then interface templates. I will add a new entry. So the interfaces, R1 is connected using Ether1, and that interface is going to the area 0. So we'll keep that value. Networks is optional, so we can keep that field empty now. The network type is going to be broadcast, and basically that's all we need. So I can click OK. So just by adding that interface template, if we go to interfaces, you can see that OSPF has identified Ether1 and the IP address in that interface, and now that interface is sending OSPF messages. So let's continue with the next device in the topology, and that is going to be R2. So R2 has Ether1 connected to the area 0 and Ether2 connected to the area 1. So let's go to R2, interface templates, and I will add the first one to Ether1 broadcast, and then the next one is going to be Ether2 that is connected to the area 1, and the type is going to be PTP. We can click OK. So let's go to the next one, and that is R3. So R3 It's kind of similar to R2. Ether 1 connected to the backbone, Ether 2 connected to area 2. So let's open R3 and let's go to interface templates. Let's add a new entry, Ether 1, network type broadcast and area 0. And then we have Ether 2 that is connected to the area 2 and the type is point to point. Now we can click OK. The next one is going to be R4 that is just connected to area 1 using the interface Ether 1. So let's go to R4, interface templates. Let's add the entry, Ether 1, area 1, point to point, and then OK. And finally, the fifth router, R5. So let's go to R5. Ether 1 is connected to area 2. So we have that over here. Ether 1 connected to area 2. That is going to be BTP. And then OK. So we have added all the templates for all the interfaces that are connected to the routers. But still we are missing the interface 2 and 3 in every router where those local area networks are connected. Those interfaces are going to be passive because we are not expecting neighbors out of those links. So we need a new interface template in R4 and R5. So let's go back to R4 and I will add a new template. So in this case, the interfaces 2 and 3. The area is area 1. Network type, we can keep broadcast, but we need to enable the passive property. And then we can click OK. Now if we go to interfaces, we can see that those interfaces have been added. They are identified, but the state is passive. They are not sending OSPF messages. The networks that are connected to those interfaces will be advertised by OSPF. So now let's go to R5 and we'll do the same. So here we have Ether 2 and Ether 3. You can see that we can add more than one interface in just a single entry that is connected to area 2 and then passive. And we can click OK. Now we have completed 4 steps in every router. So if we go and verify and test. So basically we need to see those adjacencies up and running. Additionally, those routers must be exchanging the network information across all those domains and all the areas. So let's see how that looks. For example, if I go to R1 now. So we have R1 here. Let's go to neighbors. And we can see that R1 has 2 neighbors. One is 10.0.0.3 and 10.0.0.2. And we can see the state is full in those 2 adjacencies. If I go to IP routes, we can see several routes coming via OSPF. Additionally, I can identify here the route that has been advertised by R5 and also those routes that have been advertised by R4. So it seems that everything is working as expected. So let's go to R5 and let's see how the routing table looks in this device that is in area 2. So IP routes, and we can see all those routes there. So let's try to send a ping from one of the IPs in that local area network all the way up and down to one IP from the local area network in R4. So the interface in the router is using the IP.1. The same thing is happening there. Let's send a ping. So tools, ping, and that is going to go to 192.168.1.1 from the IP that is on R5 172.16.1.1. I send a ping, so we can see that that is replying. If we go to the trace route 192.168.1.1 from the local IP in R5 that is 172.16.1.1, we can see the path that those packets are taking. So basically this is going from R5, then is going to R3, then from R3 is going to R2, and finally is hitting R4. So that's the path that traffic is taking from the source to the destination. Everything is up and running. We have successfully completed a new lab by using a multi-area OSPF topology. There are some additional features that can improve the performance, and those will be covered in the upcoming videos here in the channel. Please remember to activate the bell to be notified when that content becomes available. I hope this video has been informative for you. Thank you.